Now, this is lecture 3B1, and I want to discuss Laplace equation. But first, a little bit of introduction to Laplace equation. One of the major goals of electrostatics is to find electric field given a charge distribution rho. And we know quite how to do that. Okay, E at any point R vector, the position vector, we get 1 by 4 pi epsilon naught integral of r hat by r square. This is the distance to the field point from the source point, and this is the source distribution in the volume. Now this is a vector integration because of the presence of r hat, and often that is an extremely intractable and difficult. So we can do better than that. We now know that instead we can do a scalar integration, and instead of electric field we can find out first the potential at a position, and that does not involve the vector integration, it is a scalar integration, and so it is easier to do. However, still the integration may not be easy. Sometimes there is no analytical results possible. Of course, symmetry does help in simple cases, and that is what we are doing it as problems or home assignments. The further difficulty is that the charge distribution may not be known a priori beforehand. Here it assumes that you know rho beforehand. But as you have seen in the case of conductors, the charge gets redistributed, and we don't know. Only the total charge may be known, and hence it's a difficult problem nonetheless. It helps to therefore to cast the problem in as a differential equation. Okay, so that is as differential equation, and of course you know that that would require the boundary conditions. Okay, and we know that the divergence of electric field, this is a differential equation, which is rho by epsilon naught. This we know, and we know that E can be written down as minus of the grad of the potential. Combining the two, I can write down that the del square V is equal to minus rho by epsilon naught. Now that is indeed the heart of electrostatics. It almost includes, along with boundary conditions, okay, along with boundary conditions, I should be able to solve this and get the potential, and from there I can get the field. And of course we know this to be as the Poisson equation. Now notice that the Poisson equation involves the Laplacian or del square. Now we have to understand what is this? What is this operator del square V? Some physical feel for what does this del square V of a scalar quantity means. Let me point out, okay, with an example. This is some arbitrary scalar function, and it is plotted. I've taken this example because it has both minima, okay, and maxima. There are actually 4 corners. You can see maxima and then falls down to minima. What is plotted, this is a 2-dimensional example, and hence I could plot this is y and this is x, and this is the value of the scalar, as we had discussed right in the first lecture in introduction. What is plotted in the xy plane is the corresponding grad, okay, or the maximum slope at each point. So you can see if it is a minimum, then the arrows point in a direction of maximum increase, and it is going away. Okay, and if it is a maximum, then there is no direction in which it changes maximum, so it is almost zero. Okay, and then it will be trying to change and becoming smaller and smaller here. Okay, so this is the grad. Of course, we know that electric field is minus of the grad, and then of course there will be directions will be reversed. So if we are thinking in terms of a charge, then probably what is sitting here is a minus rho, around which that is it will be minus. Okay, and maybe there are plus charges here in two dimension. That would look like that. So del square V, in some sense in Poisson's equation, the del square V tells you the curvature is determined by the source term, that is the charge. So what the important thing I want you to note that it's in existence of maxima and minima. And you can think of the Laplacian, the operator, okay, is, as we know, is the grad of a scalar and then the divergence of the grad, okay, as the example shows above. It's something like the d square by dx square in one dimension. Okay, so del square t is like a second order derivative. And what is second order derivative physically? Which measures curvature. The first derivative is slope and second derivative is curvature. And in Poisson equation, then it is a statement then about curvature, that there is curvature is determined by the presence of charge distribution or charges. So presence of charge determines curvature. That's what I am emphasizing on. Now, in this can be seen also in a coordinate independent form, for example, the Laplacian. Okay, you remember the metric FGH. Okay, then there is a second order, but this is a partial differential equation. So first order, so there is a weight function here. In the first term, it is GH by F, del T by del U, and then the whole thing, again, partial derivative. So similarly, the three terms. And of course, in this is very simple in Cartesian coordinates, and it directly shows that it is indeed the Laplacian is simply second order differential in each of the partial differential in each of the directions. This can also be using this using this, we can always write down in other coordinate systems. I have written down specifically, okay, for the spherical coordinate system. It is important to at least remember the first one. You'll be given, but it is good to remember the first term in R. So this is 1 by R square del by del R, scale factor R square del T by del R. Similarly, you can write down the three terms. In cylindrical, of course, is 1 by S, del by del S. This is, of course, not del by del T. This is del by del S. Okay, so second order differential appearing here, second order differential in phi square with a metric S square, and of course, this is the del square d by del Z square. So what I want you to note that indeed partial differentiation, okay, it is a case of partial differentiation, and hence when you solve this, we do not know a priori how many constants will be involved in its solution. You might have already studied that in first order differential equation there will be one constant of integration, and hence I need to know one boundary condition. In a second order differential equation, I have two differential, I have second order, I have two in integration, I'll come up with two constants which have to be fixed by the boundary condition. But that's not true for partial differential equations. Okay, you sometimes analytical results are not there, sometimes that it will involve infinite number of constants because it could be a series solution. Okay, with each term having a particular constant. So Poisson equation is a partial difference equation and it's an inhomogeneous equation. That is a is always better to write it down, Poisson equation, because that is really the essence of it captures everything about electrostatics. If I've given the boundary condition and if I've given this as Poisson equation. So it's a partial differential equation. The physical meaning of this is something like a curvature of the scalar field. Okay, and this is the source term. So source term determines the curvature. Now let me go over to what instead of Poisson equation, a special case of what I would say the Laplace equation. The Laplace equation, of course, Poisson equation involves a Laplacian, but the Laplace equation is, for in case of electrostatics, Laplace equation will be del square V, there is no source term. That is, in regions where there is no charge. Does it mean that electric field is zero? No, because it means electric field is determined in charge-free region by the boundary conditions. So in Laplace equation then, it appears it's a statement about no curvature because there is no source term. And hence, no curvature meaning there will be no maxima or minima, okay, in charge-free regions. If there is charge-free regions, it cannot have a maxima or minima. That is, the functions will be monotonic. Of course, boundary conditions determine the function, as we had seen this. So to familiarize with Laplace equation, I'll take three simple cases. This can be solved even otherwise, but we should have a feeling of how is Laplace equation solved in simple cases that we already know of. But let's take up the three simple cases to illustrate the use of the Laplace equation, or rather getting familiar with Laplace equation. Now let's take two infinite parallel planes, one at x is equal to 0 with v naught, and the other at x is equal to a, which is v. They are infinite and placed a distance apart. Now let's apply these are the boundary conditions. So which is the this region between actually every other region, okay, x between 0 and a, and this region and that region are all charge free. They are free space, and we want to find out v and electric field for all space. Let us at least first focus on the space between the x is equal less than and greater than a is 0. All right. So what is the del square t in this case? Del square t, it doesn't is only one dimension. Notice that is only one dimension because the charge is there both in the full YZ plane here and YZ plane here. So the only direction in which a potential can change and electric field can change is in x direction. And hence, it doesn't make sense to, so the first term is the only term, del square t by del x square. But since there is only one variable, this will, why am I writing t? It should be the potential v and the potential v. And this is actually d square v by dx square. And between x and a, this is equal to 0. So now this equation is only a ordinary differential equation, ODE, ordinary differential equation. And the solution is absolutely straightforward. There is v of x would be of the form which is a straight line because the second order differential and it is vanishing. So mx plus c. So m is the slope, c is the constant. And we'll apply the boundary condition Okay, so that is the boundary condition should be Vx is equal to 0, which is V naught, is x goes away, so plus C, which means C is V naught. So 1 and Vx is equal to A, given it that it is potential V, and hence M A plus C already we know it's V naught. Okay, which means simply M is equal to VA minus V naught by A. So the general solution then is now Vx is equal to VA minus V naught by A x plus C is V naught. So that is the general solution, which is if I plot, okay, between if I plot between V as a function of x, then it is, let's say it's A, then it's like that. Suppose this is V naught and this is VA, okay, and this is the slope, and that is how it changes. Now, one thing is to note that the Laplace equation in one dimension got reduced to actually almost one-dimensional second-order differential equation where the curvature was 0. Since the curvature was 0, okay, the solution was a straight line. This is not specific to this case. This is indeed the nature of Laplace equation solution. That is, there is no curvature, and hence there is no maxima and minima, and it will be monotonic. And that for a one-dimensional case can only be a straight line. Suppose I had, in addition, let's say, another place where I say that it is VB. Let's say B, x is equal to B, this is x is equal to A, this is 0. So it is, suppose I go back and say that, all right, here there is, I have another boundary condition, let's say between this is B, and I have this as VB, and this is VA. Okay, so then what would be the, let me assume that somehow VV is smaller, because, okay, and then what would be, can I write down Vx now? It's almost straightforward. Again, apply the boundary condition between x and A and B. Okay, so this I can almost straightforward write down almost by inspection, or you can write down the two boundary condition explicitly, and also this will, and VA minus VB by B minus A into B. So that would be, so this will be, let's say, it will be like that again. Okay, so this is the nature of, suppose I want to know nature of the solution of Laplace equation. Now, now I can actually find out between, let's say, x between 0 and A, okay, what is E? E would be simply minus dvx by dx, okay, and that would be minus I VA minus V naught by A, is a constant. This is for x less than, greater than 0 and less than A. Now, note that because it was d square by v dx square was 0, okay, it was monotonic. I keep repeating this because this is the nature of the solution. This is monotonic, and which means no maxima, no minima. Let me also point out that suppose I knew only these 2 points. I know there is no maxima and minima. Okay, and I needed to find out the point from here. Then I could have just averaged it. So suppose I knew 2 neighboring points. Okay, this point and this point, and I wanted to get a third point in between. I just take these 2 points and make an average, and I'll get the third point. So the solutions have an average around the neighborhood. Because there is no maxima or minima, this is an average of the neighborhood. This is quite clear in the one-dimensional case, but we'll see that this is also general. In fact, that is how computer solutions of Laplace equations happen. All right. So this was to point out this nature of such solutions of Laplace equation. Let me take up another example. Okay, so let's take an example this time, and that was a straightforward one-dimensional example. Let me take up an example in which I have first solved the Laplace equation for spherically symmetric potential, which what it means is my V has only R component, no theta and phi component. Okay, suppose it is that, and so we'll solve it and use it to obtain VR for a spherical shell of radius r maintained at V naught. So let's say a spherical shell, okay, which is maintained at V naught and it has a radius r. So we'll have to solve VR for all r. Okay, so that's our, and then we'll compare this case with the uniformly charged shell carrying a charge q. At the moment, I'm not saying anything. Only thing that is being said that the boundary condition for solution of the Laplace equation is V naught. And I am demanding what is the VR for all R. If I can get VR for all R, I can also get electric field. All right. So let's quickly do this. This is simple. We know that del square V in spherical symmetric, the only term that will be of importance here, since it is spherical symmetric, would be the first term, which is 1 by square del by del r square del V by dr del r is equal to 0. That's the Laplace equation. And why is the other terms are not there? Because it is already known that VR is spherically symmetric. Now this is 0, then there's again, here you can see that I've taken a simple case that is only one variable is left. So it reduces to the fact that r square dv by dr is a constant. All right, let's that constant say C1. That constant be, let's say C1. All right, then what we have is dv by dr. I'm interchangeably writing, let me stick to the r from the origin. This is dv by dr is equal to C1 by r square. And this would imply that V of r is minus C1 by r. I'm just integrating, okay, plus an integration constant C2. And hence, this is indeed the, if there is any time potential is spherically symmetric, okay, then this is the general solution. I'm yet to apply the boundary condition. And then the boundary conditions, because it also got reduced to a simple ODE. Okay, this got reduced to a simple ordinary differential equation. This is a simple second order ordinary differential equation. Okay, so that is why we have two constants to fit, and we can, and in this case, the two boundary conditions can be, as you can imagine, one is given that V at r is equal to r is V naught, and V at r is equal to infinity, we can demand that it is 0. Okay, so that will fix our C1 and C2. So V of R is equal to minus C1 by R plus C2, which is equal to V naught. Okay, and V naught is a 0, would give you simply C2. So now we have fixed the boundary conditions. So we can write down the general V of R. So V of R now simply V naught R by R for R greater than R. Now one can compare this with the as we were asked to do for the case of a Q, a Q's total charge Q spread over a radius R. Then in that case we know what is my V. Let's call it V naught. Then that will be also Q by 4 pi epsilon naught R. So now compare this and compare this. This already we know. Okay, let's say 2 and this is 1. So compare 1 and 2. Okay, so from this we know that V naught is indeed has to be just that. Okay. Now let's go to the region which is R less than A, R less than R. Okay, so there is, so we can see from, suppose I take it the total minus C1 by R plus C2. Okay, now this take it to that. Now if R less than R, as R goes to 0, as R goes to 0, then V0 tends to infinity. But there is no reason why V should go to infinity, because there is no charge here. So no charge. Okay, and hence no possibility of V going to 0. And so it's unphysical. And hence I demand, for if it to be finite, the only way I can keep it finite V of R is demand C1 to be 0. Okay, so in that case, V R is equal to, we know the condition, R is equal to R in this case. Okay, C1 is 0, so this go to C2, but we know that this is equal to V naught. Hence, Laplace equation tells us that V R less than R is a constant, is the same constant as V naught. Okay, which means as E is R less than R, for a shell with a constant potential would be also 0. Okay, and so we can say that V of R as R less than is indeed Q by 4 pi epsilon naught R for R less than, that was V naught, we had said that. Okay, R. So notice the nature of the solution again. Okay. So suppose I had two concentric. Okay. Suppose I had two concentric. Let me just give additional. Suppose I had one was this, which was at V naught, and another was a concentric sphere, which was V equal to 0. And that is, I made it. So what would be the, how would the function look like? Okay, if I plot R as a function of V as a function of R, then let's say this is V is equal to 0, okay, and this is V naught, and this is R, V naught, so this is going like that. Okay, so the field is only between V this and that solution, and is monotonic. There is no maxima or minima, and it goes from V naught to V is equal to 0. All right. So this is a simple. So let me take up the other example, the last example, which is in cylindrical coordinates. Okay. So Laplace, I'll go through this quickly because it's exactly similar reasoning. Okay. So first we will get a general solution for cylindrical symmetry, which means it depends only on VSS, V of S. And let's consider, then we'll apply this to the case where there is two long cylinders. Two long concentric cylinders, and one is kept at, let's say, radius A, S is equal to A, and the other is S is equal to B, and B is greater than A, and they are maintained at VA and VB. So we were demanding what is V of R, E of R, okay, and then examine the case when the outside the outside one is set to 0. Okay, I'll go through this because it's exactly similar quickly. So this is the only term which depends on the radial equation for radial symmetry in cylindrical equation. So if this has to be set to 0, okay, radial part of the Laplace equation is 0, so which means this part must be a constant, say S1, then V of S is simply integrated C1 ln S of C2. Now let's consider the region S between the space between the two concentric cylinders. We apply the boundary condition V of A C1 ln A plus C2 VA and V of B C1 ln B C2. Simple two equations, and we can solve that. Okay, and that gives me that V of S. Okay, I can write down in terms of this is one of the constants ln B by A, and then I'm just find out the C1 and C2 and plugging into my general solution this. All right. So that gives me 1 by log B by A, VB log of S by A plus log B by S. If it will be minus, then it will be S by B. But this is in a form in which I fixed all the constant in terms of B and A. Okay. So VA and VB was given to me. A and B are also given to me. So this is fully between A, S, and B. I could simply take the derivative, okay, minus S dV by ds. Remember, this is also becoming a one-dimensional problem because it is a cylindrical symmetry. And I get my electric field in between A and B. Okay, so now what is this? Suppose it's a special case, VV is equal to 0. That is the outside concentric circle, I earth it. Okay, then this reduces, VS is VA ln B by A ln B by S. Okay, and then V is of S is changes, okay, as log of B by S. Okay, again, the E of S I can immediately get. So what about S less than A, that is inside the concentric circle? I can again argue similarly that VA at A is equal to VA, and VS is the general solution, S is less than A, and it again S becomes, as goes to 0, it becomes infinity, and I can again demand that C1 is not equal to 0, this is unphysical, and hence there is no reason for it to be going to infinity because there is no charge inside. So I'll demand that C1 is equal to 0. Okay, and hence Vs must be a constant for less than A. Okay, so and E must be 0 for less than A. Now let's consider the region S greater than B. Okay, so for S less than A, we had demanded that at S is equal to A, it will be VA, that is fixed, and hence going back to the original general solution, we said V of S C1, so I have to fix C1 now. Now, if I go to S is equal to 0, it tends to be infinity, of course, okay? But there is no reason why, there is no charge there, so why should it be infinity, okay? So it is unphysical, and hence we demand that C1 be actually 0. If C1 is not equal to 0, then it implies it is unphysical. There is no charge there, there is no reason why it should be, and hence C1 must be 0. So I demand that C1 is 0, and then my solution is simply that the potential at less than A inside the inner cylinder must be the same as VA. Then the electric field is less than A is 0. Okay. Now let's consider the region S greater than B. Okay. Now go back to the original solution, C1 ln S by V, and is plus VB, S is greater than B. Now again, V infinity going to infinity is going to this is expected. Why? Because we have a long cylinder going to infinity. Okay. And hence, we have to do a trick. Let us set a second boundary condition. Suppose I said that at some point C, which is greater than B, okay, is VC 0. Then my V of S, okay, potential becomes VB log of S. I add the constant log B by C. For S greater than B, this is outside the exterior region, and C is greater than B. I can now again differentiate and obtain electric field for all outside, which is what we would expect. So suppose I take the special case of VV is equal to 0. Obviously, there will be no field. VV is 0, then there is no electric field. So no field outside S greater than B. This is what we expect. If there are two concentric, let's say, cylinders with fixed voltage, and outside is Earth, then all the electric field is confined to inside the concentric cylinder. Okay, it is not into the annular region between the VA and V is equal to 0. So all these three examples I've given to make the repeated point that Laplace equation saying that the curvature is 0 leads to, in all the three cases, V is monotonic. At any point, V is the average of the neighborhood. Okay, they are the two characteristic features of Laplace equation, however complicated the situation is. I illustrated it where the partial differential equation actually reduced to an ordinary differential equation, and hence we could solve it by using the boundary condition and fixing the constants through the boundary condition. But this is true for any dimensions, okay? And even if it is partial, there are two characteristics. That is, V will be monotonic, that is, there will be no maxima and no minima, okay? So monotonic meaning no maxima within the region where there is charge free, no max, no minimum. And if that is true, then at any point V, I can take around that point, and since there is no maxima and minima, this will be an average of, we'll prove this even more thoroughly, okay, average of the neighborhood. I can take the average, and because it's monotonic, and I will get the potential there.